and good afternoon to everyone on the webinar today. We are going to go over getting started, setup, and defaults within PartMaker.
So whenever you start opening up PartMaker, there's some default features and some preferences that you should be setting first before you start programming. One of them is you'll always see this setup dialog box. This will open up. And the reason for this is before we started working with solid models, one of the first things you needed to do in SwissCAM was to set up your length of part, the stock diameter, the excess stock, the guide bushing length, guide bushing diameter. Well, that's not the case anymore. So if you don't want to see the setup dialog box pop up when you first open up PartMaker, you can turn this off through the preferences. So that's what we're going to look at first. We're going to look at the preferences. These are held under the view button, and we'll open up the preferences. The first thing you're going to want to set is whether you're working in inch or metric. We do have full metric libraries for those of you that want to work in metric, or we have inch libraries for those of you that want to work in inch. The face window name is always going to be the main spindle turn window. That always has to be first in the process table. So we automatically create the first setup window or construction plane, if you will, to be a main spindle turning operation. You could rename this if you wanted to, to say main turn or main spindle, something like that instead of front. So you would just change the name here, and that name would start showing up when you opened up your PartMaker again. Next are the boundaries here. Now, these are large boundaries for Swiss programming, but the reason that we use these large boundaries is on the CAD side of things. Let me just close that for a second, jump to the CAD side. We've got some absolute line generation techniques that come from the X0 position or the Z0 position. And any line that is outside the stock boundary as an absolute generated line will not show up. So if I've got an OD of 3.5 inches here, I can show that stock on my screen and create a horizontal line at 1 inch. You'll see it show up. But if I create a horizontal line at 4 inches, it won't show up because it's outside of the stock boundary here. Now I can take and create an incremental line, create the horizontal line at 0 first, and then I can go and say, well, I want a line that's parallel to this line 4 inches up, and pop it into place, and you'll see that it'll show up. But other than that, all absolute line generation has to take place within inside of your stock boundary. Let's get back to the preferences. So that's why we leave these large boundaries in here. If you're working with tubular stock and you work with just tubular stock, you can actually create ID boundaries if you want to as a preset. And the excess stock here is how much are we facing off the front of the part? Most operations will start with a facing operation. If you have a standard facing operation, you could just tell the amount of material that you take off as a standard face operation, and this will show up in your excess stock in your setup dialog box. Below that is family of parts programming with parametric input. This is an actual piece of older technology that we really don't use anymore because we have the abilities to import solid models. So for instance, let's say you work with SolidWorks and you have a configuration file. And that configuration file has 5 different models in it. It's the same basic shape. It's in a family of parts, but there may be different diameters or different lengths, or maybe a cross hole here or there, something like that. Instead of using family of parts programming with parametric input, you can just read the model in from the configuration that you want to work on and program that. Once that's done, you'll have a list of toolpaths on the side of the screen that makes that model. So when you need to go to the next family of parts, all you have to do is delete the model, load in the new model, and then rechain any geometry that needs to be chained. So working with solid models and family of part programming is a lot simpler than building parametric input, which is basically notepad text files. Okay, Process time, this is for whether you're working in seconds on your machine or in minutes on your machine. And then the NC program editor here, we have a multi-channel editor that's a bit available for you instead of using Notepad, which is our default. Normally we use Notepad in training because everybody has Notepad on their system. We do have a multi-channel editor that you can use, and that will split up your code, but it'll also give you the opportunity to do some code editing that a standard editor won't allow. You may have a third-party editor like Simco editor or the Predator editor or third-party application like NC Simulate, something like that. You can use those editors in PartMaker. What you will do is uncheck the multi-channel editor, and then you'll search for the editor that you want to use. In this case, I can go to Autodesk, find my HSM Works, and use the Simco editor, Autodesk Simco editor right there. Okay, or just use the multi-channel editor. Now, if you use the multi-channel editor and you get an error that says that your post processor or the machine hasn't been configured in the editor, please let me know. I can send you basically a global pass that will allow you to run any post processor in PartMaker through the multi-channel editor. The only drawback is you'll have to pick your machine out of a list of multiple machines that PartMaker supports. We've got like 900 post processors, so it may be a little while to find your machine, but I can send you that file. It's just basically a general pass that lets you work with any post processor that PartMaker will produce. Okay, so that's the multi-channel editor. On the right side of the screen, prompting to enter face window verification options. If this is checked off and I go to verify a toolpath, it's going to just flash up on the screen. You're going to see a finished toolpath. You will not see any tool motion. But by having this active, when you click on the verification button on the cam side, a little window will pop up and you'll be requested to show the toolpath, either a hollow toolpath, a solid toolpath, or stop motion toolpath. And then you can also speed up or slow down the toolpath so you can actually see it running on the part. So I recommend that everybody have prompt to enter face window verification options turned on. Next are the autosave files. This autosave feature is a background feature that is automatic. You have no control over the process once you turn this on, and the file's getting saved every 30 seconds. So if you're unsure of your programming and you want to just make sure that every 30 seconds, whatever you're doing is being saved off, turn this on. If you don't want the program being saved every 30 seconds in the background, then you will leave this unchecked and just manually save your processes through the save button in the upper left corner here once you've got the parts saved into a folder. Okay, so as you can see, I'm not using autosave files. I just have a discipline of saving my projects as I'm working on them. Next is showing the setup dialog on startup. And that's why this setup dialog box shows up. If I shut this down now, and I fire up my Swiss package, with that feature turned off, this will load, and you will not see the setup dialog box. So if you do want to see that setup dialog box whenever you start up PartMaker, you'll show it on startup. And then as we start the program again, the setup dialog box should pop up so that we can begin setting up our stock profiles. Okay, so that's the key to getting rid of that startup dialog box if you don't like to see it. Okay, displaying group numbers. This is another older piece of technology. We don't really need to display group numbers anymore because we have a job explorer on the left side of the screen. That job explorer will allow you to see all the toolpaths you're creating in the various construction planes and also list all the solid models you're using as well. So I normally don't use display group numbers either. Right below that is auto-locking toolpaths. And that means that every toolpath you create will automatically be locked. So if you need to edit the toolpath, you'll have to go back into the Job Explorer, open it back up, and unlock it before you can edit it. So I rather use the auto lock toolpath feature individually instead of a global setting, and that's why mine is unchecked. So I can lock individual toolpaths instead of having everything locked at once. Below that is your face window background. Right now we're set to a gradient color, so you're seeing black near the top of the screen and blue near the bottom of the screen. You can change that to whatever color scheme you want. If it's gradient, you can pick a top color and then pick a bottom color if you want to, and it'll change your background. Or you can just go to a straight background color, which is what I prefer, and just work within a straight background color. The sample color we're starting off with is yellow, but if you want to start drawing in a different color on the CAD side, you'll set what you want as a sample color. And then when you start drawing, you'll see that color. Okay. All right. Again, on the NC program editor side, you've got your choice of the multi-channel editor or an editor that you want to use. So that takes care of the preferences here. Now let's look at the defaults. These are very, very important. You set these defaults correctly and your programming is going to be much easier. If these defaults aren't set correctly, you will struggle in programming. So the defaults are found under Job Optimizer. And we're going to have defaults for the milling operation and defaults for the turning operation. Let's look at our turning defaults first. Starting in the upper left corner, you'll see that the whole group parameters in PartMaker, we actually separate our machining strategies. If you're turning or milling or boring, you're going to be doing a profile group or a tool path. But if you're making holes, whether it's a drilled hole, tapped hole, counterbore hole, thread mill hole, whatever it is, you'll use a whole group parameter. And that's this little option right up here, new whole group. The one thing I like to do here is to turn off the through hole. If I turn that off, when I open up the whole group, I will see tip compensation parameters. So I can compensate the drill to the tip of the drill or the diameter of the drill or the tip of the largest tool or the diameter of the largest tool. If I have this checked on, I won't see those parameter sets. So I usually check this off so I can see those parameter sets within the group. I normally do not mess with any of the diameter values or the nominal depth or the chamfer because I'm changing those constantly depending on the kind of hole that I'm trying to make. Now, when you see the word profile group in PartMaker, that is a tool path itself, a turning operation, cutoff, threading, boring, grooving, whatever the strategy is on the machine other than a hole making strategy, it's under the profile group parameters. And again, in here, I can set some defaults. Normally, the only thing I change here is the return length. On Swiss machines, you normally do not do multiple roughing passes. You'll usually do, say, a rough or a finish, or even in many cases, just a single finish pass to shape the diameter of the part. But I'm seeing machines with larger and larger diameters. There's a 42 millimeter machine out there. And rumor has it there's going to be a 55 millimeter machine on the horizon. So if you've got a 42 millimeter machine and you've got to turn a diameter down to, say, 10 millimeters, you're not going to do that in a single pass. So we have a turning strategy that allows for multiple rough operations. One of the things the strategy uses is a return length to lift the tool off the part so it can retract it for the next depth of cut. And again, on Swiss machines, I like to make sure that all my motion is conservative because the bar is moving, not the tools. So I normally set my return length at about 10 thousandths here. That gets the tool off the surface without having to draw the bar back too far. And then the tool just retracts, drops down, and makes its next pass. The return angle, I usually leave at 45 degrees. And that's so that the tool comes off of a corner at 45 degrees instead of pulling up the wall or dragging horizontally along the face we just turned. Now, surface roughness here, I would be honest with you, this is more of a virtual world thing. We could put a surface roughness value in here and then have the material calculate what it considers to be the feeds and speeds for surface roughness. But the hardware really is the final arbiter in what that surface finish is going to be. So it is not unusual, even after setting all this up, you go to your machine and you'll have to change a feed or a speed to get the desired surface roughness. That's on the hardware end, and I can't control that through my software. So I really don't bother changing the surface roughness around. I'm going to use my own knowledge of how to cut material to cut the metal. I don't want something trying to generate a feed and speed for me that I know isn't just going to work at the machine. The chamfer length, again, I'll leave at 0, and the spring pass, I just put a 1 in here so that whenever I do a threading operation, I get an automatic spring pass with the operation. So that's setting up your whole group parameters and your profile group parameters. Next, on the bottom left corner, start at cutting point and return to cutting point. These should be checked off. If my cursor is the tool and I'm pushing the bar forward so the tool can cut the part, I return to a cutting point. That means to bring the bar back to its original position. So if I start and return to a cutting point for every tool path that I create, that bar is just going to be sliding in and out of that guide bushing all day long. And that's not something I want. I want to minimize the bar motion as much as I can to make the program more efficient, but also to save the bar diameter and the guide bushing. I don't want to gall the guide bushing up. I don't want to pull back with a burr on the end of the part that could possibly wedge the bar into the guide bushing. So as a default, we don't start and return to a cutting point. These two should be turned off. Next is the thread height. Are you working with a percentage of pitch, which means we want a percentage value for the pitch value? In other words, a 50 thousandths pitch would be a quarter 20. Well, what would be the percentage of that pitch to create the height of the thread? If you don't work with percentage of pitch, but you actually use thread heights, you'll change this to part units. And this must be changed before you start programming. Once you start programming, this feature grays out and you can't change it. So make sure you're setting your thread height correctly before you start programming. On the middle of the page, apply comp in PartMaker. Let us comp the tool for you. We'll do nose radius compensation. We also do mill compensation. So by letting the software comp the tool for you, you don't have to worry about what's going on your offset page. You miss entering an offset on your offset page at the machine, we're still going to run the diameters that you want in the software, okay? So I like to apply comp in PartMaker. If I have a tight tolerance, then I will apply comp in PartMaker as a global value to get the code into the general area for the diameter values I'm looking for. And then what I'll do is I'll go into the process table and I will add compensation into the toolpath for wear compensation. So PartMaker outputs the comp code for you, and then you can adjust that code at the machine with your wear compensation page, okay, if you need to sneak up on a tight tolerance. I'm not a fan of outputting can cycles for all turning operations. This is a global parameter. So if you leave this checked on, every single toolpath will be tried to output as a can cycle. So again, I'll turn this off and then determine when I need a can cycle for turning or when I don't. Same with the constant surface speed here. I don't want every single toolpath having CSS on it. So I'll uncheck this. And then if I do have some diameters I need to work with and can get a better finish with CSS, I'll do that individually for each toolpath. My coolant is standard. That's just going to guarantee you'll always get a flood. If you have a machine that's got multiple coolant options, those options will be generated through your post processor, and you will see them in the process table as a multi-coolant button inside the process group itself. So on your defaults, just set this to a standard flood and you'll be fine. My turning units are going to be inch per rev or millimeters per revolution. So I'm going to set it to UPR. My default feeds and my default speeds, I'm not going to worry about this either because each tool is going to have its own feeds and speeds. However, if I do have a machine that allows for balance turning or for pinch turning, there's a bunch of different names for it. For instance, like a Citizen M, that comes with a gang and a turret. We want to know what you consider to be the primary tool post, either the gang or the turret. It doesn't matter which one you choose as the primary tool post, but that will have to be used first in the pinch turning operation. So if I leave my primary post to gang slide, the first tool in my pinch operation has to be set to the gang. If I was to set it to the turret, then the first tool in the tool path has to be set to the turret. Okay, so that's what the primary tool post is used for those machines that can do the pinch turning, the pinch milling. I've actually run a pinch thread for a customer. They wanted the double lead thread. I just made one pass with two tools and accomplished that. So we need to know what your primary tool post is. Groove option defaults here. Basically, I just set what I want for a retract option. I can retract by an axial step so that the tool will just step up slightly before it does its next plunge. I can retract by a set distance, so I can plunge and then retract out a set distance, or I can just go ahead and wrap it to the clearance plane so that I can peck and retract to clear any chips, get the tool flooded, that kind of thing. So you choose what you want as a default: wrap it to clearance, wrap it to a set distance, or retract by an axial step. The safest operation, of course, is always to retract or wrap it to the clearance. Okay. And then, the length of an optional feed out move and a feed ratio. In other words, if you're feeding in and you want to feed out, but you want to feed out 3 times the feed in speed, you can set this value to 3 and it'll update the feed rate to 3 times whatever your cutting speed is. Down below, input options, diameter programming. This is important to turn on. If I do have to work off a print, I don't want to have to constantly divide all my diameters by 2 to get the correct horizontal line in position for turning. The system can do this for me, so I can put in a diameter and the system will automatically output a radial equivalent. So you just read the print, diameter of 1 inch, the radial equivalent is 0.5, you'll get a horizontal line set to 0.5. The next one is positive Z programming. And this is a clever little feature that allows you to input a Z vector. You do not have, or a Z number, excuse me. You don't have to worry about a Z vector. With positive Z programming turned on, the vertical line that you're creating to position a Z move will always be correct. If this is not turned on, then you'll have to figure out, if I'm working on the main side, is the vertical line I want negative or positive to the face? If I'm working on the sub side, does that get reversed? Is it going to be positive Z to go into the face? Is it going to be negative Z to go out of the face? This will take care of that for you. So positive Z programming is a feature that allows you just to input the length of the vertical line you want in Z. And I'll just quickly jump back into the CAD side. All right. So let's go ahead and show the stock, and I'm going to make a vertical line at 0, which shows the face of the part. And I want another line at, say, 1.25 inches. In most other CAD systems, if you're working on the left side here, you would have to put in a negative value, or if it was the sub side, you may have to put in a positive value. With positive Z programming, I just put in the number I want, and it's going to show up in the right spot. Okay, so always have positive Z programming checked on, and you're not going to have to worry about any of your Z vectors. Back into the turning defaults. On the right side of the screen, the machining data here. Again, I'm not too worried about what I want for a minimum feed or a minimum UPR, unless you're working on some very small parts. This max feed here is only, you can actually set a maximum feed rate in case you're using a material and the material calls out a feed rate of, like, an F500. You can actually set this value to make sure that it doesn't do that. But we also use a maximum feed rate when we can't use G0 on the machine. If you're working in a mill end polar condition, in polar motion, Most controllers will not accept the G0 while we're in a G12.1 command, which is the polar command. So how do we get around the rapid? We put out what we call a fast feed. There's an actual variable in the post called fast feed. So once my G12.1 kicks in, instead of a G0, I'll see a G1 for a feed rate, but then the feed rate is going to be whatever I set this to. And I can mimic a rapid rate. Again, rapid feed and maximum spindle speed. Rapid feed is usually set internally within the controller with a parameter set or a bit set, but you can control your rapid feed if you wanted to. And again, maximum speed is for your main spindle, whatever value you want for your main spindle, max spindle speed, and that links to the CSS for your G96 line. Tool change time. Swiss machines are very quick at tool change times. If you are needing to put in an actual time for the tool change, remember that this is a portion of a minute. So if I put in 0.25, that's going to be roughly 15 seconds, something like that. So whether you need a tool change time or not, I normally just set 0 in here because I'm not using it. Leads, arc radius, line length, and lead angle. These are links to the tool path. How do I approach the material, cut the material, and then how do I exit out of the material? You'll notice that I have very conservative numbers here because I don't want a lot of bar motion setting up the tool for a lead in, lead out. If I have an arc radius of 0, a line length of 20, and a lead angle of 0, the tool will position itself for the cut approximately 20 thousandths away from the cutting point. If I put in lead angles and I put in arc radiuses, it'll pull the bar further back into the machine so that I can approach at a 45-degree angle and sweep in on an arc radius. And again, with Swiss machines, since the tool doesn't move, the bar's got to move. So lead in, lead outs can cause excessive bar motion, and that's why I use these values right here. Next, corner rounding. Corner rounding is just a feature in most modern controllers that will allow the tool to move between axes by using both controllers at the same time. And so if I wanted to create a nice sharp square corner with a clean edge, I want my end mill to transition from X to Z without a pause in the transition from the X to the Z vector. Corner rounding will actually round the corner. It will give you a sharp edge, but the tool stays in constant motion, which gives you a better finish. If you have an older machine, corner rounding may not be understood by the controller. So if you ever ran code and got an arc interference error on the machine, it was probably corner rounding that was doing it. You'll just come into PartMaker, turn this off, run your code again, and the machine will not alarm out. And of course, remaining stock detection, we want to know what we've cut and what we've left. So I'm going to leave that on, and that sets the defaults for turning. So again, probably the most important features on this page are to make sure we're not starting and returning at the cutting point. We've got our thread height set to however we use it, percentage of pitch or part unit. I'm applying comp in PartMaker, and I've got my options for the input and positive Z programming turned on. The rest of these options you can set the way you want, but I would not set the defaults without having these as a must item, because that'll make your programming much easier. All right, let's look at the defaults for milling. The milling defaults, again, upper left corner, I'm going to turn off the through hole button here so I can actually see the tip compensation variables, how I step my tool over if I need to make multiple passes on the end of a part or the face of the part, how I step the tool over. I have two choices. I can actually do a part unit and type in a step over of, say, 100 thousandths or 120 thousandths, whatever the value is you want to shift the tool over, or I can use a percentage of the tool diameter to determine the width of cut. And if you are using that, I would recommend your width of cut value around 40% as a default. This is set to 80%. That's pretty aggressive. You know, if I'm using a 30 thousandths end mill on Inconel or something like that, I don't think I'm going to step over 80% of the tool to try to make my next cut. We're just going to snap that tool. So as a default, I usually set it under the radius of the cutter. Just in case I forget to make that change, I know at least I've got a chance to save the tool. Okay. Now, the advanced 2D milling and surfacing defaults, if you come to our 3D training class or our advanced classes, we'll cover these features. Again, this is just to get you started, so we don't need to look at this. I will apply comp in PartMaker for all of my milling operations. We'll comp the tool for you in the code. And then again, if you had a very tight tolerance, we could activate the wear compensation within the process table so that you get the G41, G42 call in your code, and you can use your wear compensation page to dial in the tolerance. Coolant is again just a flood. Feeds and speeds, tool change, X, Y, and Z. This doesn't have anything to do with the gang because gangs don't move in Z. They have Y motion and X motion. If I had a turret and maybe I wanted to home the turret before starting a job, I may change these, but normally I don't touch these until I see where my turret is. And then if my turret's in a safe home position, I don't have to move it. If I do, whenever I use the turret, I will have some vectors that the turret will move to. Okay. Also with milling, we can modify feed rates on arcs. So if you're having trouble with chatter on a roughing or a finish pass, you can change your feed rates by a percentage. So internal arcs, you can reduce the feed rate. External arcs, you can speed up the feed rate, that kind of thing. But again, this for me is a troubleshooter. So if I'm not having problems, I'm not going to modify the feed rates. That's going to add extra code. And in some cases, it's going to slow down the machining operation. On the right side of this page, maximum spindle speed. This is for your live tools. What do you want for a maximum spindle speed on your live tools? Okay. What do you want for a maximum feed rate? Again, if we're in polar motion using a mill and I try to use a G0, I'm going to get alarm at the machine. So I'm going to put in a feed rate that I want to use for the fast feed option. Tool change time, again, it's up to you whether you want to use the tool change time. I normally don't. And then if I need to control my rapid rates, I can control the rapid rate here. The leads are, again, the lead and lead out for the mill. And you'll notice that I'm using 75% of the cutter diameter and a lead angle of 45 degrees. 75% of the cutting diameter for an arc radius is larger than is required to make sure that when I do want to comp the tool and I lead in with an arc, the arc radius will be large enough to prevent the arc interference error at the machine. So normally I set my arc radius to 51%, which is slightly larger than the diameter of the cutter. And the line length or the lead-in length, I set at 51% in case my machine needs the radius of the cutter to activate the cutter comp correctly. These are the minimum numbers I can use, which means, again, I'm preserving bar motion. And then my lead angle, I'll just leave it at 45 degrees. But if I need to change it, I'll change it for individual tool paths. Arc tolerance at the bottom here is wide open, and that's because I want to be able to fit arcs. When I take 2D geometry from a 3D profile so I can work in the 2D window if I want to, then a larger tolerance will allow me to fit the arcs better. So I just leave this alone. If I have to tighten that tolerance up, I'll do it per individual projection. In other words, when I go to project the geometry, I'll change my tolerances there for the projection. And then, of course, I'll leave the corner rounding turned on to make sure I get smooth corners and smooth finishes on the corners. And that basically sets up the defaults and the preferences. Now, one of the things that you can do when you're working with the system is to create what I call a blank template. So I've got the system set up the way I want it. I've got my color scheme set. I've got my default set. So I'm going to go File, save the job file as a blank template. Okay, so I'll just go to my PartMaker training here, and I saved the job as a blank template job and save it. So if you're sharing a computer, like if you've got a day shift and a night shift, and you come in the next day and you're looking at your preferences, and this has been set back to say a gradient, and for whatever reason they've decided they're going to program in metric. Instead of trying to go back in here and resetting all your defaults, you just need to open the job file and look for your blank template, and you're right back to square one where you left it. So I always recommend creating a blank template. So that's your start point whenever you want to do a job. Okay. All right, let's talk about importing solid models. A lot of machinists are now using solid models to program from. So our import features can import 2D wireframe, either a DXF file, which is from Autodesk, a CAD-L file, which is from CAD Key software. I believe they're now called Key Creator, and a DWG file, which is a drawing of an Autodesk file. Now, I am not a fan of DWG files. DWG files are a print of the part, which means that DWG file has the part rescaled to fit in the print, which means as soon as I bring in the DWG file, I have to strip out everything but the part I'm working with, figure out what scale it is, and then rescale it back to 1:1 so I can actually program it. So if you are receiving DWG files from your customers, just request that they send the DXF file instead. That's the actual drawing in AutoCAD, which will be scaled 1:1. It just saves you a lot of time and effort before you have to start programming on a wireframe part. Okay. So again, DWG files, I really don't like them just because of all the work I need to do to them to get them ready for programming. On the solid end, we have X_T text file transmission. This is a neutral translator. SolidWorks will translate it. Autodesk will translate it. Certain other packages like ProE or thinking what else, Dassault, those kinds of 3D modeling packages, they should always be able to output X_T as a neutral file. X_B is just a binary format of that text file. So either one, X_T or X_B, we will accept. We can work with native SolidWorks part files or native SolidWorks configuration files. So if your engineers did create a SolidWorks configuration file, which has a family of parts in it, we can read that file in and then pick which part from the configuration file we want to work on, and all the rest of the configurations will not be loaded into PartMaker. You'll get an individual file out of the list of configurations. We can also do IPT Autodesk Inventor files, native Inventor files, STL files, ProE files, and STEP files. Now, the STEP file will also import IGES. You'll notice we don't have an IGES translation. That translation is done under the STEP translator. So if somebody sends you an IGES file, you'll use this to import the IGES file. Okay, so let's underscore X_T. Let me see, do I have a part here? I'll just grab one. EM Swiss tutorial number 2. And here's the import of the X_T file. Now, again, my background color here is not something I may want. So how do I change the background colors in a solid window? Solid options, set view, background color, bottom gradient color, maybe something like gray. And you can change the color schemes on the background for the solid model. Now, in many cases, when you bring the solid model in, it's going to have an origin that's nowhere close to what we need. Okay, so if I bring in the solid model, I'll just go with vertex here, just to put the origin on some crazy end. All right, let's set that. And let's take Y at 90 degrees and rotate that. So when you read the solid model in, it may contain an origin that's not even close to what we need in order to machine the part. Now, this origin here, even though it is part origin, what we're actually doing is we're matching the machine origin. We're putting the part in the center of the guide bushing on the main spindle at X0, Z0. So if I do have an odd origin, I'm going to use the edit part coordinate system and reset the part origin. There's 4 different methods. Vertex, which will find the edge or the corner, like I did right there. Arc circle center, which you'll probably use 95% of the time, if not most of the time. And face center. Now, face center, you want to be careful with. Arc circle center is going to look for an arc or an edge curve on the face of the part, as you can see right there. And it'll find the center of that arc to set the origin. A face center, if I pick this face, the face center is going to look at the area of the face I selected and find the centroid position on the surface of the face. So in this case, it wouldn't even be close to the center line. Like on the back here, I could possibly use face center because the areas that don't have the surface on this face are equidistant and equal in size. So the calculation to find the centroid point of the face surface should put it on the center of the face here. But if one of these holes was moved off, the centroid would be down here somewhere, and that's not the center of the part. So if you need to use face center, be careful. You're picking an area to find a centroid. Arc circle center finds an arc and finds its center. So that's the easier method here. And then the last method is edge midpoint. So if there was an edge on your part, you could find that edge and it would set the origin to that edge. Okay, so we need to set the origin on the face of the part. So let's set the origin to the face of the part. If I view normal to the face plane or the construction plane I'm working in, you'll see that this is not a turning operation here. And that's because the Z vector, which is blue, is not facing away from the part. The other vector that is on the face is the Y axis. So I'm going to go to my Y axis and I'm just going to rotate it 90 degrees and view normal. That's not correct. Next. That's not correct. One more time. That's correct. We're now in a position to program the part. So that's how you read in a solid model and set its origin. Now, the next thing we need to do is find a tool library and a cycles library. I do have a master tool library. If you guys want to start with a library with about 200 or so tools in it, I do have a library file that will do that for us. If I go to tools here, I can find my master tool library. In fact, we called it the super deluxe master list because we're kind of kidding. But as you can see, there's lots of tools in here. So I could load this file. And as I'm working on the part, let's do a quick facing operation, select a tool. Let's go with this one. Okay. This is a main face. Apply and close. And now I've got a facing operation for the part. Once I've got those tools needed for this part, instead of saving the master library again, I can file, save tool as, and save just the tools that I used on this part with this part. So I can have a master tool is loaded, but when I go to save the job file in the tools file, I can save the tools file with the job name. And that way, when I open it back up, I'm only going to see the tools that I used for the job in the tool library. I will not see this huge list. Okay, same for the cycles files. When we open up a cycles files, we can have a large list of cycles, pick which cycles we want, which are the hole making groups. So if I have let's just go grab a quick cycle file here. PartMaker, PM Swiss. All right, and open up the cycles. you'll see that I have a different series of cycles in here. So I can, again, build a list of cycles, tap cycles, drill cycles, counterbore cycles, whatever cycle I want, load that into PartMaker, and then when I'm done using only the cycles that I need to use for the job, save the cycles files as, again, the job name, so that I can keep the tools, the cycles, and the job in the same folder. That way I don't have to hunt around for this stuff the next time I need to open it up. And that's what I would recommend all new users do, is keep the cycles, the tools, and the job in the same folder. Any questions on that? Okay, one last thing. We do use quite a few files. We use a job file, which is what we're looking at. We use a tools file. We use a cycles file. We also use a post processor file and a sub file. So we load the post processor, the sub file loads automatically. So that's actually 5 files, separate files that we're working with. And the reason we do that is so that we can do exactly what I just explained. Have tools that are individual to the part, or have tool libraries that are individual for each machine. You may have a Citizen and a Sagami. They're not going to be able to trade tools. The Sagami is using a larger stick tool profile than the Citizen is. So you want a separate library for your Citizen, separate library for your Sagami. How can I make this easier? Well, with PartMaker, we can create desktop shortcuts. And these shortcuts can be specific to the machine that I'm working on. I do have a sample here. I'm working with a Sagami SS327 5-axis machine. So I want to be able to just double click on this shortcut here. And when PartMaker opens up, I want to be able to have the tools automatically loaded. So my tool library automatically loads. I also want my cycles library loading for me. So I have a cycles for my machine loading that I use. I also want to have the post processor automatically load for my machine. So how is that done? Well, you'll start by creating a new shortcut or using the shortcut that's available on your desktop. Okay, so you look for the PartMaker shortcut. In this case, it's going to be the PartMaker Swiss. Just drag it out onto the screen and you'll get a link. And you'll be able to use that link. So the first thing I do is I'm going to right click and rename to the machine that I'm creating the shortcut for. Once I've got that done, I'm going to go to my File Explorer. And in this case, it's on the C drive. But if you've got more than one person programming that machine and you want to share all your tools and all your cycles, you can throw these files onto a network drive and then point the shortcut to the network drive. So no matter who's using the shortcut, you're all going to be using the same tools, the same cycles, that kind of thing. I did it locally on my C drive. I created a folder called Sagami SS327. In there, I placed the FMS kit, the machine kit, the post, the sub, the cycles, and the tool library. If I wanted to, I could go back to my desktop, find my blank template, just copy it into my shortcut folder. So that I can just go right back and say, file, open job file, and get my blank template. The template does not load automatically because PartMaker doesn't know what job file you're working with. You'll just have to go grab it. But everything else loads automatically. So once I have everything in this folder that I want for the shortcut, then I just right click and I go to the properties of the shortcut and I use the start in folder. Please do not change the target. This is what fires up the software. But as you can see, I'm starting in C:\Sagami SS327. Once I have that start in folder selected, every time you want to use the machine, all your files will load automatically. All you'll need to do is bring in the solid model or the DXF file and start programming. You will not have to worry about loading tools and cycles and posts. So again, file, open the job file. There it is right there, my blank template. Open it up And now I can just go and import a part. So let's import x_t and go to, where is my, oh, I must have had the demo moved. Yeah, I must have moved my Pocket demo. And say grab a solid model. Again, change the background color here if I needed to. And now I'm ready to start programming. My tool library has been automatically loaded, so I'm ready to go. Okay, so if you have multiple machine styles, I definitely recommend doing the shortcut. It's just really going to speed up your programming.